I would like to thank everyone who joined us again. Going back to Keynote Talks. Before our speaker will go on the stage, we discussed the thing that he wanted to talk about. And that's very exciting. A human brain is always working, and on average it spends 30 watts per hour. Artificial intelligence needs 100,000 times more energy. What is the conclusion? AI, in terms of energy efficiency, is lagging behind the humans. So there are experts who try to improve the energy efficiency of the trained model. Ivan Oseledets, the professor of physics and mathematics, the professor of the Russian Academy of Science, professor of Skoltech, the leading researcher on AIRI, the director of the Center of Technology of AI. He also has a cum laude diploma from MIT, and which specialized in applicable mathematics and physics. He was the most young expert who defended his doctoral thesis, and he received the award from the Russian president in science and innovation for young scientists. Hi everyone. Good morning and good afternoon, good evening, wherever you are. I'd like to talk about the training of large AI models. AI is moving from small models, specialized models that can only resolve one task, to large models that can use hundreds of billions of examples, and that has hundreds of billions of parameters. There are some models with almost 1 trillion of parameters, and it's used for image recognition, text recognition and analysis, generation of voice, speech recognition. This approach of integration of multimodal data is more efficient than training the models in the specialized field. When this revolution of deep learning started, there was this new summer of AI. It was enough to use 1 or 2 graph cards for training, and it was possible to receive some great results based on that. You can do the same right now for some particular tasks, but if you talk about really large models, like GPT class models, GPT or DALI Kandinsky, that were trained in Russia, they can be trained only by a company. Only a company or a large organization can afford that, with tens of thousands of GPUs. And obviously you need to develop a specialized software for that. You need a lot of compute for that, and that's a lot of energy that you need to burn. That leads to CO2 emissions. For example, GPT-3 model that was trained in 2019. So this model that has 175 billion parameters used to be a leader in OpenAI, the company that that is quite famous, that is called Open, although it's not really open because the parameters are hidden. And for several years, it used to be the largest model that was trained. Now the situation has changed. If you talk about language models, there are these huge language models that were trained. But if we go on a car from Earth to Moon, that would be the CO2, the equivalent of CO2 emissions. Or that would be the emissions of large cities, of entire cities. And the emissions of entire cities are comparable to some of the trainings of the models. The results of these research efforts move us closer to multitasking, to AGI, because the models that generate images or that generate images based on the descriptions, text descriptions. They are like some mid-level creatives, because the neural network can draw a logo that would be the same in terms of quality, as it would be drawn by a graduate, a mid-level graduate of some mid-level university. You know, this creativity, we thought it was impossible for the AGI to achieve, because we talk about creativity, we talk about the creation. Whether it is creativity or not, that's another topic. But anyway, a machine draw something, a human draw something, you know, is a kind of a visual representation, and there's less and less differences, and the designers, the advanced designers, I started to talk about them for some reason. Anyway, they started to use AI as their tool, as one of their tools. If you go back to the technical part of my research, there are two challenges we need to resolve. They are very much related to each other. First of all, the computational time. The times for the training might be hundreds and thousands of GPU hours. We will need 100,000 hours if we use only one GPU to train one big modern model.
Clearly that is not possible. It will take a huge amount of time, and you also need space for storage of the model parameters, and also all the interim computational results have significant memory limitations. So we are moving from the 40 gigabytes of memory graph to a 100 REM graph card. We will be able to train more models, because this REM limitation is one of the key limitations. In fact, we do not know, well, if we do it up front, we will have to resolve the storage problem. With the GPT models, the GPT family of models, what we have is the architecture of the network is the same, a transformer-type architecture with three types of blocks: the linear layer, the attention layer, and that's it, basically. What you can increase is the number of blocks, the size of blocks. An interesting thing happened. The architecture of this transformer type can very successfully tackle text processing, image processing, better than other neural network architectures. So basically, we found the architecture that can tackle all kinds of problems. This same architecture can also be augmented with image processing, video recognition and understanding, and many more things. But to get better quality, better performance, we of course need the right data. With images, for example, we can just extract all kinds of images from the internet or satellite images. Let's suppose we have solved the problem, we have dozens of billions of images, we add augmentation to that, and now we need to increase the size of the model so that the model can memorize and interpret, understand the knowledge in the data set. The architecture is there, it is fixed. Of course, people keep coming up with boosts, with some better additions that augment the performance, but still the transformer is already working pretty well. It doesn't mean we won't have an alternative anytime soon to that transformer. It's just that what we see now is that the increase of the number and size of blocks results in better performance. These are the figures with the modern model, blue model, the biggest one, trained by the whole world. Many of you have probably read online in social media the diagrams of its training, lots of engineering tricks to help train this model. But roughly speaking, the estimate is 400 GPU A100 120 days for training. Kandinsky training took 4 months with half the Christofari capacity. Delhi 2, its training time reaches 200,000 GPU hours. So we are talking about gigantic numbers. And there is no evidence that says that those numbers will not be increasing. There is a thing with training this kind of models. How do you assess efficiency? We calculate the number of operations with a floating point that need to be done, and then we calculate the time. GPU of the latest generation could handle 300 to 400 teraflops, the peak performance of these GPUs. The latest software, if you optimize it, where the speed of data transmission between different nodes is very, very high, what NVIDIA has been doing, you can achieve the 30 to 40% performance of the peak. So, to sum up, there is a foundation for increased performance, even with the peak models, the peak GPUs. Even if we're talking about systems with dozens, hundreds of graph cards, GPUs, there the performance, of course, will be a bit lower. And this is precisely what I wanted to talk about. How do we take the hardware that we have available and use it to increase the performance of training of models? 2 parts to my report. The first part will be dedicated to the commonly used concepts, and the second part will be about the results that we have in our research, what we are currently working on, and our future work. The obvious idea is that you need to do calculations in parallel. You need to align them. If the model is too big, if we want to have a certain amount of GPUs, you just divide calculations between the different graph cards, and that's the way to accelerate computing. For many years, what we were doing was data parallelism. So we have a big data set, we split it up in chunks, and each graph card calculates the gradient in its chunk, the data parallelism. The interval of gradient calculation in a selected area, in a selected chunk, is paralleled, but then you need to take all these parallel gradients, sum them up, calculate the final result, and then send the results to each model. So each GPU contains its own copy of model parameters. If the model has 100 billion parameters, the memory will need to be 4 times bigger. If it's half that, then 2 times bigger. That parallelism will simply not be able to be packed in the GPU memory. If we simply do data parallelism, we will have to cut up the model in chunks. That's with model parallelism. Direct distribution neural network is a sequence of blocks that receive input information and then process this information one by one. So we split up our model in horizontal pieces. So until the first piece processes this information, the second piece cannot come into play. It needs to be a sequence. So this pipeline parallelism, this sort of a conveyor belt, could be a problem. Another type of parallelism is when you split up your model in vertical pieces, divided in different GPUs. It could be a sophisticated system, a number of nodes, 8 GPUs in one node that communicate well, another node with slower GPUs. So it's a classic problem for parallel programming. The world of ML and data science has been ignoring this problem for a while, but now we need to go back there. We need to get back to that problem, try to solve it, or we need to wait for some one-button solutions where you press the button and there's magic, everything works. Of course, there are people working on relevant frameworks, but it needs further investment of our time and effort. Now, reduction in calculation time, that could be done with parallelism. As for memory reduction techniques, there are several techniques used actively in production, but as a matter of fact, What is probably not known to the larger audience is that the optimization of such approaches is very mathematically intensive task. One of the standard tasks is activation checkpointing. This is where, well, I'll go back to that in a minute. Or it could be offloading, where you upload parts of the model weights to the CPU that could be 10 times bigger in terms of memory than parallelism. Very briefly about data parallelism, one exception there: when we divide the data set in chunks, we have to calculate for each part of the data set its own gradient, its own batch. That is equivalent to training with a big batch, 100 GPUs. The batch is 100 times bigger. So we want to avoid the relevance, the corresponding increase in the number of iterations. So that means you need to select the right learning rate. We have the solution. There is an optimizer called lump-Lars, which essentially scales the gradient. And for example, in 2019, the BERT model was successfully trained using a large batch, 76 minutes. That's the time the training took, based on TPUs. Same goes for clusters with big GPUs, but with TPUs, the size of clusters is way bigger. And now back to memory. The most critical moment, actually. We have a model with a certain number of parameters to calculate the update of the model parameters. We need to calculate the gradient of the model parameters. So we have a certain number of blocks, and in order to produce a gradient, we need to store all the interim results, the activation before each block, and the memory that is needed for that such storage, especially if you have a large batch, could be 10 times bigger than the number of parameters. Let's say you have the GPU of 100, the maximum number of model parameters, 1.2 billion of parameters, even if you use half of the accuracy, because these activations that I talked about will eat up all the memory. So 12 M bytes memory will be required. Deep Speed Framework, I have to mention it, developed by Microsoft, because this is an efficient yet simple way to divide model parameters among computing units. People use this framework very actively. We need to distribute data among different computing units. First, we calculate the distance, then the gradient, and the number of communications radically reduces. The model can be split, as I said, vertically and horizontally. A few words about the pipeline parallelism. This is related to our current project. So, as I said, we just do it up front. Most of the GPU will be just idling. The idea here is you take a batch, you split it into micro batches, and then the calculation becomes asynchronous. So we split up the computing in different batches and we do it asynchronously. I think this is the most promising approach, and we needed to do not just at the level of the batch, but also all the parameters that are involved in the model. There are other approaches, the pipe dream approach, where the utilization of the GPU with the vertical with a vertical split becomes much higher. I said there's a lot of math in it. You will ask me, well, where is the math? This is just engineering, pure and simple. Where do you split the model? In which blocks? It depends on the complexity of the block. It depends on the complexity of communication. There is this great doctoral thesis by Alanishev. If you're interested, feel free to look it up. Very interesting. NP full, NP complete is the allocation problem, so you can just suggest characteristics. Same goes for checkpointing. This is where we need to understand which activations need to be maintained. with direct and reverse transfer, we don't have to store all the interim calculations. We can just store part of them and then recalculate the rest. So where do you draw these lines? Which ones do you store? Which ones do you not have to store? This is a problem for mathematical programming. And this requires pretty complex heuristics. Checkpointing, usually with checkpointing, we just take every third layer and we store them. The rest is not stored. But then there are effective software solutions that regular data scientists do not use in their work because, well, one of the reasons is because they are not very well known and the button is not very convenient, but the rotor program component is really great. Similar situation with the offloading of part of data from the GPU to CPU. So if we are lacking in memory in our GPU, we can offload it to CPU and, if necessary, reload back to GPU and be complete once again. We could come up with interesting heuristics for it. Zero infinity, for example, is an implementation case with just one GPU. Same goes not just to weights, not just for weights that could be offloaded, but also activations. If you have a situation where batch number 1 cannot be fit into the memory, we could do the activation offloading. What else can be done to reduce consumed memory in training? I will be talking about two things that we tried, that we tested. The first thing, and I think this is our achievement, I'm very proud of it, the idea is very simple. In the architecture of neural networks, there are activation flow functions. You've heard about ReLU. GeLU is what you use here. You need to store the flow derivative of this activation in all codes. This is how it's done. You store the full bit representation. What we're showing is that you don't have to store bit-by-bit representation or approximation, or you could just have this sort of a shelf to approximate a number. You need an 8-value table. This is how you can reduce the memory for training and memory for storing the parameters with actual models. 15 to 20% less memory, which is great in terms of training. We have managed to identify similar solutions for the linear layer and also for reducing consumed memory in attention. And another concept that we have been developing, we looked at all possible techniques used at the moment, and we saw that each and every technique can be improved, but to get maximal performance, we needed our own training framework. We needed to create one from scratch. We are looking at the blocks that we're using not as integral units, but each matrix is split up in smaller batches. We write a completely asynchronous multiplication of these batches and blocks. And so, let's say one multiplication is not yet performed at a certain layer, but part of the multiplications have already happened in some other batches. It could be represented as a diagram. PyTorch, TensorFlow, they do not exactly give us the right level, low level. Low level might sound a little primitive, but it's not primitive at all. Anyway, you can represent it as such, as this diagram in mathematics. Developing such frameworks takes a very long time, where we have each computational unit getting its super small sub-problems, which we distribute among different units. The units do not have to be homogeneous. Let's say we have some old GPUs, K80, K80, K40, and we want to use them for something. And we also want to automatically balance the load to ensure maximum efficiency. And it turns out it can be done. So we took this idea. Once again, what is the idea? We take standard neural network layers, transformer architecture, linear layer, norm layer, attention. For each of the layers, we implement this strange Frankenstein monster-like asynchronous multipliers. So we do the multiplication, but it's asynchronous. And if we can use the products of the multiplication later on in a subsequent layer, that's great. So that's the gist of it. We used as a planner the StarBU library. It's an openly available library. And we take this library and we write our own in C++ from scratch. It is a huge undertaking within the project of AI Center for Environmental Stewardship. We are developing this within the project on Green AI. Green AI meaning an AI that does not consume the megawatts of power to train, so this has direct economic benefits. It took us roughly 6 months to effectively implement the basic layers, and by now we have pretty much implemented the elementary cycle of training, elementary block transformer, but writing, experimenting, testing, prototyping, this is a huge endeavor. We have to really dig deep inside the process of training. People who work in ML, they don't really like to do it for obvious reasons. I think we've done a good job. This is what it looks like. Matrix multiplication. We do not really even split up the problem by batches. So we have the input data set as an Andron matrix, the size of the data set by the number of features, and then when you split it up into batches, it don't have to be the same size. This is done by the planner.
This is how one layer looks like in terms of the compute graph, asynchronous graph. This is one layer of the transformer architecture. It looks quite heavyweight, yet this is how it works. We can use heterogeneous systems. It's great to show how a big model was trained with this story, but we have the maximum productivity for GPUs. You can take outdated hardware that is just staying there, but you can get a pretty good performance out of it by launching several GPUs, and it will work properly. We'll have a low-level framework, and we'll make an interface with Python so that it is user-friendly and users can train models. And maybe not 30, but at least 70% of efficiency would be a great thing to achieve. Thank you for your attention. Thank you, Ivan. Very simple, newbie questions, really. How many hard drives would you need to store the information of the largest NN model in the world? You'll need a lot of hard drives, several hundreds of terabytes. But, I will have to bring it with... I could bring it with me. It's large, not in terms of the volume, but, to train it... You will need a lot, if you put all the computation racks, or this entire meeting hall, conference hall, might not be enough actually. But if you want to use this model in some real life situations, for instance, for translation of the text or face recognition, you might not need this entire hall, but maybe a few racks to launch it and how can you make a model closer to the human brain? Actually, about the training of the model, as far as I understand, you have a new task. You're the experts, the researchers, so you were able to train the model to resolve one task, and now you need to train it so that it can resolve several tasks at the same time. For instance, to recognize the image, the text, and the voice at the same time. You will need years for that? No, not years. Even in our conference, we have a competition organized by AIRI. It's called Fusion Brain. That's the task, to create the super mega model. This is this is the task that is being resolved across the world, and these models will be able to resolve multiple tasks at the same time. If the number of models increase, maybe it will yield some results. Yield some results in our country. In our country, yes. On this conference, actually, yeah. The question from Athena. The decrease of the number of the high performance, and then will it affect the edge computing? What are the developments here in edge computing? Well, actually, edge computing lies in the paradigm that I talked about. We slice our compute in many small slices and distribute them across the weak computational devices. So, like, how do you do that? Using the smartphones, for example, but it is all based on algebra, on some basic algorithms, and these methods can be used there as well, for the edge as well. Maybe you will have to work for several years, quite actually, to this end, but we'll be able to achieve that. So as I understand, the models are being trained quicker and quicker, right? Yeah, it is trained quicker and quicker, and people, being greedy, they want to increase the volume of the model 2 times, so that it learns even faster.